Swayam Prabha. Digital India. Educated India.
We had been discussing this relation between the entropy and the probability, and we actually arrived at a very important relation that S is equal to K ln W. So, relation between entropy and probability is something that is celebrated in thermodynamics and statistical mechanics and in science in general. So, that is relation between is S, the entropy of a macro state, and that is related to K, a Boltzmann constant, at times log of W. So, this S is basically the entropy, a macro state of a thermodynamic system, and this is called the number of microstates. So, now how this relation affects the other relations in thermodynamics. So, that is the question that I will try to answer in this particular class, and how this relation. So, the relation between entropy and probability, how that particular equation actually affects or its relation to other properties of the system. So it basically it's a relation to thermodynamics. So, relation to or further relation to thermodynamics. So, for this what we are going to do, we consider a macro state of a system, consider a macro state A1, a macro state A or 1 that is given by S1, a macro state of a system, and another say 2, and I consider another macro state S2. So, S1 and S2 are the entropy for this state, entropy for the system 1 and entropy for the system 2. So, S1 and S2 are the entropies of the system 1 and 2, and each I can write S1 is K ln W1 and S2 is another system K ln W2. So, now they are separated, they are separate systems, and suppose I connect them in a way that I have a composite system. So, what we do, we connect the two systems to have a composite system for which I have entropy for which S equal to S1 plus S2. And you see that if every S1 is a function of energy E1 equal to K ln W1 energy E1 and S2 entropy of the system 2 with energy E2 is to K ln W2 E2. So for the composite system, this is my total entropy and total energy for the composite system E equal to E1 plus E2. Now, when you connect the two systems, then there we need that there will be exchange of energy, entropy, and anything, exchange of heat flow and this thing. And finally, it will settle down to a state which we call an equilibrium. So, what is the condition for equilibrium? So, after exchanging the energy, after the exchange of energy, etc., the system, the composite system settles down to an equilibrium state. So, what is the condition for that equilibrium? The question is what is the condition for attainment of this equilibrium? Now, to pursue this particular question, what we can do is the following. We know that this entropy is characterized by a probability. So, the total entropy, so we do not know about the total entropy. Total entropy is basically the sum of the two, but we start from a product of the probability of W1 and W2, because this has the probability W1 and this has the probability W2. So, we consider a function W, and that is equal to W1 E1 times W2 E2. Consider a W of this form is a product of the probability for the composite system. So, if this is so, then I can search for the condition when that probability does not change with time, if the probability is maximum. So, what I can do, if the equilibrium condition is attained, I can assume that the probability will be the maximum thing, the maximum possible arrangements will be there. So for equilibrium, so for the condition for the condition of equilibrium, we may set del W del E1 equal to 0. That means if we differentiate this equal with respect to E1, so that automatically fixes my E2, because E1 plus E2 is equal to a constant. Then this condition gives me the condition of equilibrium, as we may assume, because at that point this W will not be changing. So we assume that there is an equilibrium. So if this happens, then if we differentiate it, then what does it mean? That it is del W1 E1 del E1 so I write it W1 E1 equal to W2 to E minus E1. So if this is so this is W2 E minus E1 plus del W1 E1 del W2 E minus E1 del E1, that is equal to 0. Or you may rewrite it del W1 E1 del E1, then W2 E minus E1 equal to minus of W1 E1 del W2 E minus E1 . Now you interchange a bit. So I write it, I take this W1 and in the other say left hand side under as a denominator. So it is 1 by W1 E1 del W del E1, and that is equal to minus of del W2 E minus E1 and del E1 times 1 by W2 E minus E1. So this means there is a minus sign. So on this side, you may note that we have the energy conservation, that E equal to E1 plus E2, a constant. Therefore, I can write dE D1 equal to minus dE2. So I rearrange it in a slightly different form. E1 del W1 del E1, that is equal to this minus. If I replace this with del W and del of E2, then I cancel out this term. That is, so W2, I may write it as E2 del W2, I write it as E2, and this is del E2. If I take care of minus sign, and this minus sign gets cancelled out. So I have an interesting condition, or I may write at d of ln W1 E1 del E1, that is equal to E2. So if I multiply both sides by k, then what we get? Del of k ln W1 E1 del E1 equal to del of k ln W2 E2 del E2, and this k ln W1 and k ln W2 are basically basic entropies of these two states, that's S1 or S2. So it means I have del S1 del E1 equal to del S2 del E2. So this is the condition which can be obtained for the equilibrium, because we started with the thing that we have a separate systems S1 for which I have a definite energy and entropy for one, and this is another system for which have a definite entropy S2 and other energy is E2. So when I bring them in contact, I have a composite system. I allow the system to exchange everything between them, and we anticipate that there will be an equilibrium that will be reached finally. So what is the condition for that equilibrium? That was the question. So I started with this, that if I maximize the total entropy W for the composite system, which is the product of the two, then I set that this does not change with the variation of energy, then that gives me the condition. And of course, this is subject to another condition, that E1 plus E2 is equal to constant. Subject to this condition, that brings out an relation like this. So this is basically the derivative, and what these derivatives actually mean. So this is the derivative of entropy, but S is defined in terms of the S is equal to K ln W, Boltzmann definition, where we connect the macro state with the micro state, and you are getting a new quantity. So what this quantities means? So clue that you get immediately from the usual thermodynamics, that you know that. So how to obtain this quantity? So a clue from the thermodynamics is this. So I just want to know what this condition is. So we know that combination, say the first law is dq reversible equal to dE plus P dV, and second law I stated to be the dq reversible equal to T ds. So T ds is basically dE plus P dV. So that brings me immediately to the definition that del S del E is basically 1 by T. So if you consider a constant volume, so it is obviously it is 1 by T. That is the definition that immediately comes from the combination of the first and second law. So that gives me the usual phenomenological definition of temperature. So this quantity, I see that this S1 and S1 and S2, they are related to the number of microstates, but this variation of entropy with the energy gives me an equality for the individual subsystems of the composite system, and that must be related, they are equal. So I can connect these two with a parameter 1 by T, and that defines my temperature of the system. So equilibrium means that you can define a temperature in this way, so that is the condition of equilibrium. So this is the condition for attainment of so that defines also that for each the individual subsystems, if these derivatives are equal, if these derivatives are equal for this one and this one, if they are equal, then for the composite system, then I can equate it to a quantity 1 by T, and that defines your condition for equilibrium. So there is immediate connection to thermodynamics that I can guess from this formula, and this is basically the another relation that can be that gives a very fundamental question of what the temperature is. So temperature, definition of temperature also follows from the consideration of the connection between the macrostate and the microstate for separate subsystems, and when they are connected and when the equilibrium is attained, I can think of this kind of a parameter which connect both the systems in this way. So that is the condition, that is the definition of a temperature. And with this, I close this particular part of the end of the discussion of entropy and probability for the session, and thank you all for your attention.